we are studying from here, from permeability and this red underline topics. Now, okay, before understanding permeability, we should understand something that is called as a soil and water, and why water will pass through the soil, or otherwise what are the particular names of the water present in the soil. Okay, and once again I am reminding you, I am not going very deep up towards the concept because we have to attend a paper 1. Paper 1 means 1 mark question preliminary exam. Okay, now in paper 2, when we study paper 2, then we will go very deep and will solve many problems. Now you have to understand theory perfectly and small problems which can be solved by without calculator. Okay, and those problems we have to concentrate. Now write down water in soils. Water in soils. Okay. See, let us consider this is a soil, and the water present in the soil is named a different way. That is, it might be structural water, adsorbed water, capillary water, groundwater, infiltrated water, pore water, solvent water, adsorbed water, structural water. Like that, we have many names. Those definitions we will go through, so that 1 mark question, if anything is asked in that one, then we can solve easily. The first one is free water, or gravitational water. Both are same. Free water or gravitational water. Free water or gravitational water means, let us consider this is your earth, and this is your soil, right? Now inside this soil there is a water. Inside this soil there is a some amount of water. This water with gravity it will be dropping down. Means the water which can be attracted by gravity, that is called as gravitational water. That's it. Okay, now then some water inside that will be held against the gravity, that will not count in the free water. Free water means freely available water by the gravity. Freely available water by the gravity is called as a free water. This is first one. Then another one is held water. Held means what? The soil is holding that water against gravity. Therefore, this is called as a held water. In this held water, we have three types. The first one is a structural water. Structural water. Second one is a adsorbed water. Adsorbed water. The third one is capillary water. Capillary water. Now we will understand structural water. Let us consider this is a soil. Soil is usually a chemical composite, right? Chemical composite. Chemical composite means here there might be aluminum, there might be hydrogen, oxygen, then ferrous, then magnesium. There are many elements will be there inside. If any element inside, if anything formed like this H2O, then that is called as a structural water. Okay, this structural water we cannot drain it out by gravity, or even when I squeeze water, when I put some static load on the soil, then this water cannot be removed. Okay, now this is called as a structural water. If this structural water is removed from the soil, soil will lose its actual property. Very important. If this structural water is lost, then soil will lose its actual property. When we do oven dry method, then in the oven dry method we are applying 110 degree plus or minus 5 degree centigrade temperature. This temperature is enough to evaporate the other water except structural water. Means structural water you should not evaporate when you make a dry, when you make a soil dry. Therefore, this structural water is very important water, and that will be main responsible for the structure or strength of the soil. The second one is a adsorbed water. Now let us consider a clay. See, this is a clay particle. This is all about clay particle. If I take this clay particle and put in the microscope, then that microscope will result us this rodded shaped structure. Actually, clay particles will not be a sphere one. The clay particle look like a rodded shape. Okay, like this. When this is considered as a clay particle, then its surface will be negatively charged. Surface will be negatively charged, and the ends are positively charged. Let us consider this is a H2O water. Then H2O means what? O1 and 2 hydrogens. This is hydrogen, this is hydrogen, this is oxygen. Then hydrogen is positive and oxygen is negative. Therefore, here what happens? This water will come and stick like this. Okay, this water will come and stick like this. Then water will here this side, the negative will be here, and water will stick like this, and here the water will stick like this. Okay, this water cannot penetrate through the soil. This water will not penetrate into the soil. It will be on the surface of the clay particle. Therefore this is called as a adsorbed water. This is adsorbed water. Understood? Now this is a clay particle. Then another water, this is minus, no? Then another water may come here and it may sit like this. Right? The another water may come here and sit like this. Like that, we will be having many layers on the clay particle. First layer, second layer, third layer, fourth layer, fifth layer, like that. But here, if you concentrate on this first layer of the water, this first layer of the water, this is called as a rigidly held water. Rigidly held water, or this is called as a adsorbed water. Understood? This is rigidly held water. Then the other surfaces, whatever we have, that is freely held water. That is freely held water. That you can consider it as a free water. That you can consider it as a free water. Understood? Then these two layers together, it is called as a diffuse double layer. Diffuse double layer. Understood now? Clay particle is always a predominantly negatively charged. Only ends are positively charged, and water is a dipolar. Very important. Water is a dipolar. Means this will have both positive and negative. Therefore, it will come and stick to the clay particle even in the negative surface and in the positive surface. But the first layer, whatever that will be sticking on the clay particle, that is called as a rigidly held water. Then the other one is a freely held water. Then both together it is called as a diffuse double layer. This is all about adsorbed water. Now coming to the capillary water. What happens in the capillarity? Let us consider this is a soil particles like this. It is arranged. This is arranged in this way. Okay, it is arranged in this way. Let us consider a water with a blue mark. Water might be here. Water might be here. We have studied this water at the top, the layer of the water which is in contact with the atmosphere will possess one property. That property is called as surface tension. That property is called as surface tension. What is the meaning of surface tension is this particles which are topmost layer, they have a tendency to jump. They have a tendency to jump. Similarly, this water has a tendency to jump upward direction. Then when up to its capacity it will jump towards the upward direction, then this phenomena is called as a capillarity, and this height is called as a capillary height. This height is called as a capillary height. Means capillarity is all about surface tension. When water has a more surface tension, then capillarity will be more. Understood? Now this water from here to here, whatever that water is there, this water is a capillary water. This is capillary water. Then another name we have, that is a groundwater. Groundwater. Okay. Groundwater means if this is a soil with the ground level this much and the water available below the water table, This is called as a water table, and below the water table all the water is called as a groundwater. Okay, then if any water is present here, that is not a groundwater. Be careful, this is not a groundwater. There will be moisture here, but this is not a groundwater. Water below the water table is called as a groundwater. Infiltrated water. Infiltrated water, next water is infiltrated water. When there is a huge rain, then at that time the water will be penetrating through the soil, and it may reach water table or it may retain in the upper part of the soil, but this all water is called as a infiltrated water. Okay, infiltrated water may become groundwater or it may be held in the soil, right? Next, pore water. Next one is a pore water. Pore means what? Pore means the voids present in the soil. Let us consider these are the soil particles. Then I have some void here. Then the water held between the voids is called as a pore water. This water is called as a pore water. Okay, now these are the names given to the soil water. Right? Okay. Next we will go ahead. Next, we will go ahead with the capillary water. Here in the capillary water, we have some important questions that I will explain so that one mark question can be answered. Put a heading capillary water. Okay. You already know in fluid mechanics we have studied this one. If this is a water table or this is a water level, then if you put a small, a thin that glass tube, then the water will come here and it will rise up to certain level, and this height is called as capillary height, right? This capillary height, we have a equation that is 4 sigma cos alpha divided by gamma w into d. D is the diameter of the pipe, alpha is the angle made by this water at a meniscus, then sigma is the surface tension, 4 will come in the derivation, gamma w is the water density, then d is the diameter. This is height of capillary height. But specially alpha equal to 0 for water, therefore cos 0 is equal to 1. Then you will get a equation 4 sigma divided by gamma w into d. We have a 4 here, then water this one um, surface tension for the water is always a constant, that you can note it down as a 75.6 into 10 raised to minus 8 kilonewton per centimeter. You remember this one. Then water density is also known to us, 9.81 kilonewton per meter cube. Then D will be left. If you solve this one, then you will get a 0.3084 by D. This much only you have to remember in soil mechanics. That is, capillary rise in the soil is equal to 0.3084 by D. Then what is D? What is D? Can anyone tell? In soil mechanics, what is D? No idea?
Diameter of the tube.
Diameter of the tube. No, in soil there won't be any tube, no? That is
Steel rod, sir.
steel
Steel rod.
rod. No? Why steel rod will come in the soil mechanics? No idea? D is a diameter of the voids present in the soil, because this capillarity will be taking place in the voids, therefore D is a diameter of the voids present in the voids present in the soil. Understood? Now, how to calculate this voids present in the soil? For that we have to have some empirical formula. or something, no, so that we can calculate that diameter of the voids. For that we have a formula. Write it down. Diameter of the voids is equal to 0.2 times d10. D10 is considered as a effective diameter of the particle. Effective dia of particle means you will do the C1 analysis. After doing C1 analysis, you will get one graph. Then in that graph, you take a 10% in y-axis, cut that graph and come down. Then whatever the particle size you are seeing here, that is called as a D10. Then this D10, if you multiply 0.2, then you will get a diameter of the voids. Diameter of the voids, if you substitute in a 0.3084 divided by d, then you will get a height of water in a particular soil. Okay, now this is all about. We have another formula for diameter calculation, diameter of the void calculation. That is a d cube is equal to E into d10 cube. This is also you can remember. There are two formulas. One formula is this one, and another formula is this one. Here E is a voids ratio, and d10 is the effective diameter of the particle. By using these two, you can calculate diameter of the voids. Then after that, you can calculate capillary height. Understood? Now we'll go to the permeability. Now we'll go to the chapter permeability. Right. What is permeability? The word itself says perme plus ability. Okay. The word is perme plus ability. Means that is the ability of a ability of a soil to permit the water is called as a permeability. Ability of a soil to permit the water is called as permeability. This is studied by Darcy. Darcy is a scientist who studied permeability. Understood? What he has done experiment that we have to understand so that this chapter becomes very easy. He considered one soil sample with known area, cross-sectional area, and soil sample with known length. He will consider. Then he will attach two pipes here. The one pipe here that is inlet, and another pipe at the outlet. Then outlet will be here, then water will be coming out, and this is the inlet. Let us consider this inlet is connected to one water tank. This inlet is connected to one water tank. Right? This inlet is connected to water tank. Don't worry about this water tank and how the water is stored and all. Don't worry, that I will explain later. Now here what happens, this is soil. Now you have to tell me if this is a height of the water standing against the soil, then this is the length and this is the area, cross-sectional area. As I increase the water head, as I increase this head from here to here, from here to here, from here to here, then the velocity of the water flowing through the soil V will increase or decrease. As you increase the h value, then velocity will increase or decrease. What happens to V? Any idea?
Increases.
Okay. As the head increases, then velocity will increase. Means this is one conclusion that h is directly proportional to V. Right? Then we have another experiment. This time what I do, I will keep this height constant. This height is constant. This time I will decrease this length. Means earlier we have this much of soil and later I will reduce that soil to this much of length. Or later I will reduce that soil to this much. Then this much. Like that. If I decrease the length, then the velocity what happens? If L is decreased, then velocity will what happens? The velocity will again increase. Means we are getting h is directly proportional to velocity. Then sorry, we will write it like this: v is directly proportional to h, or v is inversely proportional to L. We have got these two relations in this experiment. Then together if I write it like v is directly proportional to h by L. this conclusion I will arrive. है This h by L is nothing but the slope of the water head here is this much and water head is here this much. If I draw one curve here, then the angle made by this with the horizontal is considered as I. Then I is a hydraulic gradient, that is your opposite divided by hypotenuse, sorry, adjacent. That is tan I equal to I h by L. Therefore, this h by L is nothing but V is directly proportional to I. I means hydraulic gradient. Then proportionality constant I will introduce here, that is V equal to K into I. What is this K? K is a proportionality constant. K is a proportionality constant. And that K you can call it as a coefficient of permeability. Coefficient of permeability. Understood? From this what we understood is, as height increases, velocity increases, as length increases, velocity decreases, as velocity increases, I increases, right? Then these conclusions we got it. Now I will ask you one question, that as velocity increases, what happens to the permeability? Can anyone answer? Because you have equation V equal to K into I, right? Now tell me, as the velocity increases, what happens to the K? Any idea?
Increases.
Increases. Any other students?
Increases, sir. Increase.
Increases. If options are given like increases, decreases, remains constant, then which one you will select? Increases?
Constant.
Constant. Why constant, Varun?
Sir, proportionality constant, it's
Very good.
fixed, sir.
Very good, very good. This is the confusion they will create. By seeing the equation, you should not answer like V increases means K increases. No. Why? Because V, when it increases, no, then I will increase. When this increases and this increases, then the in between the intermediate term, that is a K, is always constant. Therefore, you increase H or decrease L or increase velocity or increase I. These all things, whatever you do, then K will not be affected. K will not be affected. Now tell me how to increase the K then. How to make the soil more permeable. Then permeability depends on what? Now I told you that the permeability does not depend on head. Permeability does not depend on, coefficient of permeability does not depend on head. Coefficient of permeability does not depend on the length of the sample. Coefficient of permeability will not depend on I. Coefficient of permeability will not depend on velocity. But then coefficient of permeability depends on what? How to increase the permeability? Any idea?
Property of sample.
Very good. Property of the sample will increase the permeability. Why? Because you have to always remember, I will go to the property list. Okay, in last class we have discussed about that. See here, the property of soil I am studying here. In this property of the soil, the engineering property I have listed here, the first one is a permeability. Then what is permeability? If anyone asks, then permeability is a property of the soil. Property of the soil means you change the property of the soil, then you will get the change in permeability. Then I will write this permeability. For that I will have some different equation, that is E cube divided by 1 plus E C d10 or D, then gamma W divided by nu. This is the equation of permeability. Then here E is a White's ratio, then C is the shape factor, then d is the diameter of the particle, dia of particle, then gamma w is the density of the water flowing, then nu is the viscosity of the water, then viscosity in terms depending on the temperature of the water. Now you come to know that K, this permeability, is depending on these all parameters. If you increase White's ratio, then K will increase. If you increase the shape, shape means whether they are rounded shape or angular shape or flat shape, roded shape, that will come here. Then the diameter of the particle, if you increase the diameter of the particle, permeability increases. If you increase the density of the fluid flowing, permeability increases. If you increase the viscosity, permeability decreases. If you increase the temperature, then temperature will affect your viscosity of the water, then viscosity of the water will affect your permeability. Like that, the permeability can be altered by using these factors, not the earlier one. Therefore, Darcy suggested that V is directly proportional to I, V is equal to Ki is a Darcy's equation. Understood? Now, in fluid mechanics, we have Q equal to A into V. That this is called as a continuity equation. Correct? Continuity equation. Then in this equation, if I substitute V, then Q equal to KIA. Okay, V means KI, then A will be as it is. This equation you consider it as a KIA. Understood? Okay, this is all about permeability, coefficient of permeability, and Q, that is a discharge through the soil. Okay, do you have any doubt? Anything you want to ask here? Okay. Now, here, whenever we study this V equal to Ki or otherwise Q equal to KIA, this one whenever we study, we assume that the sample is like this, then this is the area of the sample, then this is the length of the sample, then we will be connecting the pipe here and that water will be coming outside and the water will be entering here. But one big mistake what we are doing here is we are considering the entire area, cross sectional area. We are considering A means entire cross sectional area. But this is not actual. This is not actual. What is actual? Actual means we have to consider area of voids present in the cross section. Voids present in cross section. See here, this is your cross section of the cylinder. Then here you have a soil like this. This is a soil like this. Then the whatever the white color you are seeing in this one, that is considered as a voids. Whatever the white color you are considering in this circle, that is small whites are there. No, they are considered as a voids. Then the water will come through these voids. No, the water will come through these voids only. Then why you are taking the entire area in this equation? Therefore, this become wrong. That's why the velocity whatever we obtain by this equation, that velocity is called as a fictitious velocity. Fictitious velocity. Fictitious means false. That is your false velocity. False velocity. That false or fictitious, you can consider it as a superficial. That is also superficial velocity. These three are same velocity. Understood? And if you consider, now you have come to know that the voids only you have to consider. Instead of that, you are considering the entire area. Then you have committed a mistake here. That's why to rectify that mistake, to correct that mistake, the scientists started taking the area of the voids. When they take area of the voids, then they will come with another equation, that is a discharge velocity is equal to coefficient of percolation into I. Then they will introduce a new that constant that is considered as a coefficient of Kp is a coefficient of percolation. Then how we arrived this equation, that is a different matter, that there will be a big derivation for that. Coefficient of percolation. Okay, now you have two equations, v equal to k into I and vs equal to kp into I. Then here you can have a derivation that equation like vs divided by v is equal to kp divided by k. Then what is this vs? Vs is the actual velocity. Actual velocity. Vs is nothing but a seepage velocity. Seepage velocity. Vs is nothing but a true velocity. True velocity. Then this one you write another name for this one, that is the superficial discharge velocity. Discharge velocity. Understood? Then after this we will derive one more equation, that this will be continued, that as a 1 by n. N is a porosity, that we have discussed in the first chapter. Understood? Now you have got true velocity, false velocity, percolation and coefficient of permeability, and porosity. These all are linked together so that you can solve any questions related to that. Right? Now I have introduced you a Darcy's equation. No? I have introduced you Darcy equation. Then Darcy equation is not for soil. Remember, Darcy equation is generalized equation. Generalized equation for what? Generalized equation for any porous media. Darcy equation is for generalized for any porous media. But fortunately, soil is also a porous media. That's why Darcy's law is applying to the soil. Then there might be some limitations for this Darcy's law because we are introducing Darcy's law to the soil mechanics. Therefore, those limitations are the flow of water must be laminar flow. Laminar flow. Okay, Darcy equation will be valid when the flow is laminar. Right? Now the same way the second then how to define this laminar flow, then we have a equation, Reynolds number equation. Then Reynolds number will give us for laminar, turbulent and transitional flow. But we ask a Reynolds, then what is the equation for this one laminar flow, then he may give big numbers. But here for soil mechanics or any porous media, if Re is less than or equal to 1, very important, Re is less than or equal to 1, then that is considered as a laminar flow. Okay, this is a that limitations. Now tell me this is a gravel soil. You have to answer, this is a gravel soil and this is a clay soil, small particles clay soil, or it might be a clay, or it might be a sand some extent, or it might be a silt soil. But this is a gravel or boulder soil. Then in which soil the flow is turbulent? In which soil?
Clay soil.
Any other guess? In which soil the water is turbulent? Hmm? Turbulent ಅಂದ್ರೆ ಹೆಂಗ? That what?
Turbulent, sir. Turbulent.
In which?
Gravel soil.
Very good. In
Gravel.
gravel soil there will be turbulence, no? Because wide space is very big. Wide space is very big means the water will rush very fastly. Therefore, this is a turbulent. That's why most of the time we are not using. Okay, most of the time we are not using Darcy's equation for gravel and boulders. But Darcy's equation easily we can use it for clay, sand, and silts. Okay, na? Next, sorry, in the last one equation I have made some small mistake. I think. Here small mistake is there. Correct it. D square it is. D10 square it is. Okay, D10 square. Okay. Now, right now we have understood the permeability and coefficient of permeability, coefficient of percolation, discharge, Darcy's law, and these all things we have understood. Now we will go further. How to determine this permeability in the laboratory? How to determine this permeability in the laboratory? Not only in laboratory, how to determine permeability, that we will see. Coefficient of permeability, how to determine? For this, we have three different methods. The first method says that the permeability can be determined in the laboratory, the permeability can be determined in the field, the permeability can be determined in by indirect method. Indirect method. Then permeability, how we will determine in the laboratory? This laboratory determination can be done in two different ways. That is the constant head method, and permeability by variable head method. Then in the field, we have a pumping out test, pumping out and in, pumping in. But pumping in test, most of the time we are not doing, therefore, which is not included in the syllabus also. Pumping out test frequently we will be doing, we will discuss about this one. Indirect measurement of permeability. That will be by consolidation. Consolidation. Okay, na? This consolidation we are discussing tomorrow, and today pumping out test and constanted and variable head test we will discuss. Okay, na? Now we will go ahead the constant head method. Constant head method. Constant head method, there is a big derivation. That derivation we will remember in the when we study for paper 2. Right now, constant head method means just we have a equation, that is the coefficient of permeability is equal to QL upon ATH, where this is your diagram. There will be a water tank, and that tank is connected to the soil, and that there will be outlet. Here nearby the outlet we will be having a jar, and this jar will record the water, that is your discharge quantity of the water collected at a particular time t, that is your q and t. Then this is the cross sectional area a, then the length of the sample l, then height of the water maintained in the constant head tank, that is your h. If you substitute all of them in this equation, then you will get a coefficient of permeability. Then again I am telling you, don't judge the coefficient of permeability based on these parameters. Don't say like a t decreases. Don't say that k is directly proportional to q, directly proportional to l, directly proportional to a. Don't say like this. These are all not material property. These are all just a experimental setup. Therefore, k will be constant. That's why in your laboratory you will determine by varying all of these values. Then at the end, what you do, you will take an average of that one. That's why the k is depending on something else. Those relations are in other planet. These are just temporary relations. Right? Now we have understood the constant head method. One very important thing about this constant head method you have to remember is constant head method is very suitable for coarse grained soil. Constant head method is suitable for coarse grained soil. You just easily you can remember this starts with the C and constants with starts with the C. C coarse, C constant head method. Now we have another method that is called the falling head method. Falling head method. Okay, another name for this falling head method is variable head method. But we'll remember falling head method F. This starts from F, and this is suitable for fine grained soil. This is suitable for fine grained soil. Fine means falling, fine means fine, F means falling, F means fine grained soil. Then here the head will be varying from one height to another height. This will be decreasing. Therefore, H1 and after that H2 will be there. But this decrement is there. No, this decrement is logarithmic decrement. This is logarithmic decrement. That's why we will have a log in the equation. That's k equal to al upon at ln natural log h1 divided by h2. Sometimes if you don't write as a ln, then you can introduce 2.303, then al upon at. Then instead of ln, then you use a log 10 l1 h1 by h2. This is your k, coefficient of permeability by falling head method. Understood up? Do you have any doubts here? Okay. Now, coefficient of permeability determination by field method. By field method. Before studying a field method, we will remember we have to study some terms. Those terms are related to well hydraulics or otherwise hydrology. You know? For that we have to study. Now look at here. Let us consider this is your ground. This is your ground. Ground means what? It is made up of what? It is made up of soil. This soil may be whatever it is. It might be gravel soil, it might be clay soil, it might be silt or sand. Any one of these or combination of these or proportional of these soils will make your ground. This is confirmed. Okay. Now let us consider gravels first. Gravels are very big particles with big wide size. the wide size also very big. Then if I put a water this side, then this water will pass through easily. Okay, this water will pass through easily. Gravels will not hold water. Agree? Gravels will not hold water. Right? Now one thing I have concluded. The another thing I will consider. Then I will consider sand particles. Sand particles are very small in size, compared to gravel, small in size. Now what happens if I put a water through this one? I'll take a red color. This water is passing through this one, but immediately this water will not pass down. It will be held something here. The water will be held here. Water will be held here. Okay, if I put a little pressure to this one, if I put a little pressure to this water, then this water will yield. Held and yield, both are happening in this soil. Right? Now means gravel soil will not hold, and it will continuously yield. This is not called as a yield also. Why? Because it is not holding. Means how can I say that it is yielding? Right? It is not holding means it cannot yield also. Therefore I am not considering it as a, or just gravel means that is just porous. No? Then I will consider another soil. Let us consider a clay soil. This is a clay soil. Then when I consider this clay soil, the clays are very, 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 very small particles. No? The clays are very, 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 very small particles. The small particles with the charged atoms. Particles are always charged. Then we have studied that particles are charged means what type of charges? Predominantly negative charged particles. Then when I allow the water to pass through this soil, then the water will be held inside. Then most of the water will be held inside. Okay, when I put a pressure from here and from here, when I put squeeze this one from both the end, whether this clay will yield the water? Whether this clay will yield the water? No, this clay will not yield the water. Why? Because this water is rigidly held. Most of the water is rigidly held. Most of the water is rigidly held, therefore this will not yield the water. Now come back here. This is your soil. This is your ground level. In this ground level and in this soil, you don't know which soil is here. Gravel, clay, silt, sand. Which one is there here? We don't know. Based on that, we have four terms. The first one is aquifer. The first one is aquifer. The second one is aquiclude. Aquiclude. The third one is aquifuse. Aqui Aquifuse. And the last one is aquitard. Aquitard. Aqua means what? Aqua means water. Aqua means water. Okay, na? Now, based on these things, say for example, if any soil is there, that soil will hold also and yield also. Then that is called as aquifer. बहुत होशियार आदमी. This person will hold the knowledge and he will yield also. Most of the you all of you are preparing for exam. You should be like aquifer. Now you are absorbing the knowledge. Then in the exam hall you have to yield the knowledge. That's why you are called as aquifer. Good students are like aquifer. Aquiclude. Now, can you tell me which type of students are aquiclude? Hmm? There are few students, they are like aquiclude. They will hold water. They will hold water, but they will not yield water. They will not yield the water. Means there are some students, they will absorb knowledge. They will take all the knowledge. They will understand each and everything. But in exam hall, tuss, they are aquiclude. Aquicludes. Then what about aquifuse? There are some students, they are like aquicludes. Example, these students, sorry, aquifuse. Now we are discussing about aquifuse. These students neither hold nor yield. This knowledge they will not understand. Yeah, permeability, yeah, what we don't know, we are not understanding geotechnical is tough. They are thinking that they are not holding the water, and in examination hall they will not yield the water. They are called as aquifuse. Then aquitards. Anyone? Aquitards.
No holding, no healing, sir.
That is aquifuse already open happened. No?
Okay, okay, sir.
1 minute.
Seawater, sir.
No, I am exactly not getting. I am also not getting searching. Aquitard. Just now I forgot. No holding, no yielding. That has already happened. Aquifuse. And aquitard means
Sir, it's a semi-pervious, sir.
semi-pervious.
It's
Uh-huh. Formation
slowly
rather
yielding
nature that transmits the
food.
water at slower rates than the aquifer. Okay,
It's
okay. This,
slowly yielding of water.
yes. I understood this one. This I can consider it as a silt. This I can consider silt. See here, yielding of water is there, but with a lot of pressure. Say for example, this best example for aquitard is your curd. From the curd you will do Shrikand. You will prepare Shrikand. How you will prepare Shrikand? Because in the curd a lot of water is there. That water you have to remove. Then how to remove? You cannot squeeze that one. You will put one stone on the curd. This one, that curd. You will make some arrangement and you will put one stone for longer duration. Then after that, slowly this water will come. Then this curd is considered as it is sufficiently holding the water, but when it comes to yielding the water, it is not quickly yielding, it is slowly yielding the water. That is called as aquitard. you know that I have remember it like retired people will be there, no, they are like aquitard. They will have a lot of experience, they will have a lot of knowledge, but yielding means they will slowly yield the knowledge. That we can remember as a acquitard. Now, the intention of explaining these four terms is the best. This one we have to continue with the aquifer. Aquifer means that will hold the water and that will yield the water. Okay. Okay. Now, this aquifer, there are two types of aquifer. Okay. Now, aquifer means sand. You just remember sand as aquifer. An example, it might be a combination of sand, silt, or some amount of gravel. It might be, but let us consider most of the portions are sand. If this aquifer is confined between two rocks, this is one rock and this is another rock. Okay, then you have a sand bed here or aquifer here, and this is able to hold the water and yield the water. Why? How I can say it can hold or yield the water? Because the water table is available at this height. Very important. The water table is at this height, but you have this sand inside. No? You have the sand inside, then this is called as confined aquifer. Confined aquifer. Okay, now this is confined aquifer. Then we have another type of aquifer. Let us consider this is your rock. This is your rock, and we have a sand or something like this here. This much of sand or sand bed or aquifer is there. Let us consider water table is also available at this point. Water table is also available. The top portion is not confined. The top portion is not confined, therefore it is called as a unconfined aquifer. Unconfined aquifer. Right? We have studied confined aquifer and unconfined aquifer. You know, most of the time I will explain it like confined aquifer is something like girls. You know, girls. Why? Because they have a tendency to hold the water, hold the knowledge, and they have a tendency to yield the knowledge also. But they might be confined between the two hard rocks. Therefore, they are called as a confined aquifer. Then the unconfined aquifers are like boys. They can hold the water and their boundary is at one level only. The other level they are free and they can yield the water. This is just an example. Don't take it as a philosophy. Just to remember this one. Then we have another type of aquifer. You remember aquifer means one student who can hold and yield. Aquiclude means he can hold but not yield. Aquifuse means not holding and not yielding. Aquitards means holding but yielding very slowly. No? Four type of student example I gave. Then there is another student who look like holding the water, but actually he is not holding the water. When he start yielding the things now, then after 1 hour or 2 hour, all his knowledge will be empty. That is called as a perched aquifer. Perched aquifer. Perched aquifer means, let us consider this is your ground. Then inside one big rock is there like this. This is a big rock is there here. And the water is stored at this level. The water is stored here. Then you don't know whether rock is there, water is there. That you don't know because you are standing here on the ground and looking the ground here. Then what you do? You will put a borehole here. You will put a borehole here. Then after that, you will put a borehole and you will put a motor and you will pump the water. Then you will get a water. Then you might think that yes, you got a very good borehole. Then after 1 hour, no water from the borehole. Okay, after 1 hour, no water from the borehole. Why? Because this water is completely gone. That is already pumped out. Then after 6 hours, then again water table will come. Again water will come and collect here. Then the pump will again work. This is called as a perched aquifer. Perched aquifer means the water is somewhere temporary. Water is available near the rock. Okay, near the rock depression, that is considered as a perched aquifer. Now we have considered these all aquifers, and we have to determine permeability. Now, for that permeability determination, we will do one experiment that is called as a pumping out test. Pumping out test. Pumping out test is very interesting test and very big test. This will give you a field permeability value. Okay, here you will be having a trial borehole. This will consider as a main borehole. Then nearby the main borehole, you will put a trial borehole. Let us consider main borehole will yield you discharge Q, and main borehole will have that all the values with H, capital H or small h, then with that one, this is a big concept, I'll just give you an equation so that we can remember, right? Because we have to go ahead also. This equation you can remember, that is q equal to pi k h square minus small h square divided by log of r by r. Okay. However, we don't have a calci in the paper one, therefore this much big equation they will not ask. No, this we can remember in the paper 2. Okay, remember this one, they may ask you directly question, but problem they may not ask. Then this equation we are using it for unconfined aquifer. Then we have equation for confined aquifer, that confined aquifer equal to, that is a q equal to 2 pi t 2 pi kb 2 pi kb into h minus h divided by log of r by r. Okay, here we have a k, no, this value k is there, that is your permeability. This k is a permeability, means q discharge, because you are putting the pump on the trial borehole, then you are pumping the water, therefore that is q. Then this is the r, radius of your that you can consider as r1 and r2 also. This r is the radius of your borehole, r is nearby borehole, then h is the inside the water height, and this is the water height in the other borehole. Like that we will be having these known values, then only unknown value is a k value, that k value you can determine. This is called as a determination of permeability by field method. Okay, this theory is called as Dupit's theory, not Uppit's theory, it is Dupit's theory. Hmm? Dupit's theory. Just remember the name. It's not Darcy, right? Here Dupit will come. But K means it is a Darcy. Darcy is also there. Dupit is also there. Okay, now? Now we'll go ahead with the permeability. Okay. Yes. Now the permeability through stratified soil. Permeability through stratified soil. Stratified soil means, let us consider the soil is not of the same nature throughout the depth. This is a depth. There might be one different soil here, that another different soil here, another different soil here. Soil is different means what? Permeability is different. K1, K2, K3. Okay. The soil is different means permeability is different. When soil is different and you are allowing the water to pass through the soil. When water is passing through the soil, then the water will go parallel to the strata. Therefore, I will consider it as a K parallel. K parallel. Then K parallel, how to determine the permeability? Otherwise, the average of these all four. Is it a direct average or is there any specific reason for this one? For that, K parallel equal to K1 Z1 plus K2 Z2 plus K3 Z3 divided by Z1 plus Z2 plus Z3. This is your K parallel. Then sometimes we may have a condition like this also, no? For example, this is one soil and this is another soil, this is another soil. Let us consider this K1, K2, K3, because three different soils are there, different permeability is there. Now this time what I do, I am applying the water like this. Then the water is going perpendicular to the strata. The water is going perpendicular to the strata. When water is going perpendicular to the strata, then K perpendicular is equal to Z1 plus Z2 plus Z3 divided by Z1 by K Z3 by K3. This is your equation. Okay, this is your K parallel and K perpendicular, right? Okay, till now we have discussed about the permeability. We'll go to the syllabus. Now look at here, the permeability we have discussed. Permeability, coefficient of permeability, determination of coefficient of permeability, then confined and unconfined aquifer are names of aquifer. Now we will go to the effective stress concept. Okay, effective stress concept. Look at here, this concept is that investigated by or studied by Terjigi. This is just you think here, because I don't have much time to explain about or express about effective stress. Actually speaking, the effective stress, when it is introduced in the geotechnical engineering, then only we have started constructing a very big structures like Burj Khalifa, you know, those big structures. If you don't have this concept, effective stress concept, then you can construct a Taj Mahal. Then what is the difference between Taj Mahal and Burj Khalifa? You know why I am comparing Taj Mahal and Burj Khalifa? Because Taj Mahal is also a very big structure, Burj Khalifa is also a very big structure. But Taj Mahal here, that is a very big structure with big walls and big foundation, you know, very deep foundation. See, inside this much is there, then above that only you have this much of building, then this is called as a Taj Mahal. But the Burj Khalifa, more than this height they have built it, and very thin walls, thin slabs, thin pile foundation inside. You know, these all things. Why? Because here a effective stress concept is introduced. Pore water pressure, how much exactly the soil is absorbing the strength, taking the load. These all things are studied, and wastages are removed. The many wastage, big depth, big width, okay, those things are minimized. Therefore nowadays we are able to build very big structures with effective foundation. Therefore, why? Because the effective stress concept is introduced. Then what is exactly the effective stress concept is? Let us consider a soil here. This is a soil. Then soil has a voids here, and the voids is filled by water. This void is filled by water, correct? Now what happens when you apply this force, top and bottom? What happens? This water want to escape. This water will automatically will escape. Okay, then this load will be resisted by, that load will be resisted by what? These soil particles. Okay, when that water escapes, then only the water, this soil, this will be load will be resisted by the soil particles. Okay, now if this structure, if I make something confinement, like I will put one more wall here and one more wall here, then what happens? This inside the water is there, no, that water cannot escape. Here this water cannot escape. When this water cannot escape means, when I apply some load here, this water also resists the load, and particle also resist the load. Therefore your total stress whatever you are applying here, this total stress is resisted by your particles as well as pore water. This is the concept of effective stress. Then what is effective stress? The effective stress means the particle alone, how much they can resist, is total stress minus pore water pressure. This is your effective stress concept. Okay na? Usually how to determine this total stress? Total stress is nothing but gamma respect to gamma into height. Wherever you want, that is your height. Then how to determine effective stress, how to determine pore water pressure, that is the gamma W unit weight of the water into that particular height. Then how to determine effective stress? Effective stress is nothing but sigma minus u. If you substitute these two equations here, gamma, usually total stress, because you are studying effective stress means what? Water is soil is saturated. Therefore, you can write it like a gamma sat into H. Therefore, gamma sat H minus gamma W H. If you take H common, then gamma sat minus gamma H, then gamma sat minus gamma H according to Archimedes principle, that is your gamma dash into H. This is your sigma dash. Right? This is a effective stress concept, and in this concept we have a very huge and big problems, but you just remember this equation only, because in 1 mark question they can ask problems on a simple equation only. Okay, now we have to remember 2 to 3 points here. Look at here, sigma dash effective stress equal to pore water pressure minus total stress minus pore water pressure. Understood? Now always think here, this effective stress, total stress will be something constant, because the variation is where the variations are happening. The variations are happening inside the soil, no? The variations are happening inside the soil. Inside the soil variations are happening. Then what about this one outside? This outside sigma is always constant, because you have applied 100 means 100. How this 100 is resisting? 100 can be resisted like a 70 plus 30. 100 can be resisted like a 50 plus 50. 100 can be resisted like a 10 plus 90. Or it might be resisted like a 100 plus 0, or it might be 0 plus 100. Okay, therefore this 100 means 100 only. This is your sigma dash plus u. Okay, means you have to think about these two. Now from this you can consider, if sigma dash is increased, this is decreased. If this is increased, this is decreased now, then this will increase. Correct? Therefore from this I can conclude here, as the effective stress increases, then pore water pressure that has to decrease, or pore water pressure decreases, effective stress increases. Okay, this one conclusion I can make. The another conclusion here is, when this this effective stress and pore water pressure, they are inversely proportional. Then what about this pore water pressure? Pore water pressure depending on what? Pore water pressure depending on water table. As the water table increases, pore water pressure increases. As the pore water pressure increases, then effective stress decreases. Those things you can remember it like that. Some conclusions you can make it. This is all about effective stress concept. The last one we have quicksand condition. Quicksand condition. Quicksand condition. Look at here. Just you have to remember this diagram. If you have a soil here, and that bottom of the soil is connected to one water bottle. Let us consider this is connected to some water bottle here. Now here water is there, and here soil is there. There are some arrangements made here, some porous is made, therefore don't worry about this one. Now let us consider the height of the water soil is L, and height of the water maintained here is H. Okay, use your common sense and answer me that if this water bottle is increased, what happens? Then head will increase. If this height is increased, then this head will increase. When this head will increase, then the pressure from here to here will increase. This bottom pressure will increase. Bottom pressure increases means water penetrates fastly. Then water penetrates fastly means water will spill out. Correct? Because this height is increased, then this will spill out. Okay, then if I decrease this height, then what happens? I will explain with the green color. Now this height is decreased means this water bottle come down, then there will be a decrease in the pressure, Decrease in the pressure means water will not spill out. Water will be just storing here or this level or this level. Water is not spilling out. Now I have to maintain such a condition. Now I have to maintain such a condition that water should not spill out also and water should not come down also. Okay, then water should spill out, should not spill out, and water should not come down also. Therefore, that condition at that time what happens? Then some particles will go upward, some particle will push downward, upward, downward, upward, downward. Therefore, this is called as a boiling action. This is called as boiling action. Now, it is exactly in scientifically it is considered as a soil boiling. Okay, this is considered as a soil boiling. Then it is called as a quicksand condition. Some authors call it as a quicksand and some authors call it as a soil boiling. Then how to get an expression for this soil boiling? You know, how to get an expression for this soil boiling? For that, the same diagram I am drawing here. This is your length of the soil. Then this is your water and this is your head of the water. Okay, now consider the effective stress at this point. Effective stress at this point is equal to sigma dash. Sigma dash at this point from the top it is gamma dash into L, and from the bottom it is gamma W into H. This condition we have to achieve at this time. Means from the top also same pressure, from the bottom also same pressure. Means at this point effective stress equal to 0. Effective stress equal to total stress. Effective stress equal to total stress. Then at this point, no, effective stress equal to 0 it is. Effective stress, for effective stress equal to 0. Okay, that I will prove it here. Effective stress equal to 0 means what? Total pressure minus pore water pressure. Okay, when this equal to 0, then what happens? Then total stress equal to pore water pressure. Then pore water pressure is nothing but gamma W into H. Then this total stress is nothing but gamma into L. Gamma into L. Then from this we will derive an equation. By considering these conditions, we will derive an equation. That equation is gamma dash by gamma W is equal to G minus 1 divided by 1 plus E. Okay, this is nothing but H by L. That is nothing but IC, extended equation. This IC is called as critical hydraulic gradient. Critical hydraulic gradient. Why it is called as critical? Why? Because at that time boiling is happening. Water neither spilling out nor going down. Therefore, that is called as a water is boiling. Therefore, it is critical hydraulic gradient. Then factor of safety against critical hydraulic gradient is IC divided by I exit. Now, what is I exit? This I exit will come in the GT2 or seepage analysis. GT2 or seepage analysis. This seepage analysis is not included in the current syllabus, therefore we will not discuss. If time permits later, if exam postpones, then we will go through some of the portions. Right up. This is your quicksand condition. Do you have any doubts? If you have any doubts, you can ask. Otherwise, we'll go to the question answers. Any doubts here? No doubt? Okay. Now we'll go to the questions and answers. Before that, we'll take a small break. Now it is 9:48. 5 minutes break will come at 9:54. 1 minute ಆಯ್ತೀಗ 9:54 will come back. Right? See here, properties, classification of soil, permeability, seepage analysis. Everything is studied. Therefore, about 160 questions are there. Most of the questions are solved. Which are unsolved, those things we will go. That the rounded questions are already solved. Unrounded questions only I am going through so that I can solve all the questions. I can make all rounds, right? Now here we can answer this one. For a granular soil with increasing voids ratio, critical hydraulic gradient. What is critical hydraulic gradient? That is IC equal to G minus 1 divided by 1 plus E. Now, can anyone answer? No? ಬಂದಿರಿ ಬಂದಿಲ್ಲ
Sir, it's constant, sir.
No, here voids ratio is given, no? You increase the voids ratio, then IC will decrease. IC will decrease.
Sir, but there is a specified specimen length is sir.
Specimen? I did not understand.
Specified length of this sample. Sample length is constant, sir.
No, that is constant. No, that is not mentioned here. Okay, you can make it constant also. See, the length is constant, and cross-sectional area is also constant. This is also constant and this is also constant. But you can increase and decrease voids ratio inside, no? How? By compaction and
Sir,
by losing the soil.
Sir, sir, when increasing of void ratio, there is no change in specimen length, sir.
Yeah, increase in voids ratio, you are not changing the specimen length, but you are making the
Sir,
loose.
there is a sir, but there is some amount of soils are present in sample, sir. Specified length of sample. Then the remaining will be constant. Hydraulic gradient is constant.
No, that I will explain you like this. Look at here. Hydraulic gradient, that is I equal to H by L. Correct? Then we have I equal to G minus 1 by 1 plus E. Two equations we have. This one equation and this equation. Okay, this equation is depending on height and length. For this critical height, I can consider critical height and critical length. These two are constant, therefore I is there, that is constant. But this IC can be varied by varying the specific gravity. This is very interesting. When you have this dams here, then you will provide a filter here. At this filter, your main aim is to, even though gravel is there, gravel of same specific gravity and voids ratio is there, you have to compact it or loosen it so that IC is increased. You have to increase the IC here. Even though your dam height, water height is constant, filter length is constant, but your aim is to increase the IC. How to increase the IC? Then you have only option left is a changing the voids ratio, because you cannot change the specific gravity. Then you can change the voids ratio. How to change the voids ratio? By compaction. Then do some compaction. Then by doing that compaction, density increases. Density increases means voids ratio decreases, or loosen the soil, then increase the voids ratio. Do whatever, then after that you will be altering the IC value. Therefore, I can say that it is depending on H and L. But when you are talking about IC, then it has a both end. This end also is there and this end is also there. But in the question, they have not mentioned any other specifications. Just they have said the granular. I think you are clear.
Yes, sir.
Hmm. Next, the physical property which influence permeability are the physical property which influences physical that permeability are viscosity will influence the permeability. Yes. Unit weight only. Very
Yes,
important.
sir.
Only he is saying no, therefore this is wrong answer. Okay. And unit weight only he is saying no, therefore this is wrong answer. Both viscosity and unit weight, no, therefore this is right answer. Right? None
Yes,
of the
sir.
above will not come. Okay. Next one is this question will come to the next chapter, but still we'll answer here because we'll not come back. The shearing strength of the cohesion-less soil depends on. Cohesion-less soil means sand. Sand shear strength means if you are aware about the equation, then only we'll discuss. Otherwise, we'll go to the next chapter. There we will study. But still, tau is equal to C plus sigma tan phi. Then this is a sand cohesion less soil means C equal to 0. Therefore, your shear strength is depending on sigma and tan phi. Therefore, here come here dry density, rate of loading, confining pressure, all of the above. Okay. Dry density, as the dry density increases, shearing strength increases because this is depending on the phi. Rate of loading, yeah, rate of loading is also depending confining pressure. Here confining pressure I have to consider this and this both are influencing your shear strength, then the indirectly rate of loading also influences. All of the above will be the correct answer. Okay, now next, the standard penetration resistance in very stiff clay is lies between very stiff clay they are saying, therefore 2 to 4 will come, will be the answer. Then quicksand is, just now we discussed, quicksand is a type of a sand. No. Flow condition occurring in cohesive soil, very interesting. Cohesive soil they are saying. Flow condition occurring in cohesionless soil, all the above. Now look at here. I'll explain that quicksand condition once again. See this quicksand condition, when I was explaining, I have considered this one. Then we'll use a red ink. Now this is considered as a soil. No, this is a soil. Okay, this boiling action has to happen. Boiling action has to happen. No, going up and down here I explained boiling action. This boiling action will happen only in sand. Okay, if it is a clay, then boiling action will not happen because there will be lot of pressure building up in the clay. From the bottom, water want to come up, but permeability in the clay is very less. Therefore, water cannot come up. Therefore, there will be lot of pressure building in the soil. Therefore, there won't be any boiling action. That's why you can
My
remember.
voice is not audible properly.
Voice is not audible. What about others? One minute.
Sir, that same question explain one more, sir.
Which one?
Sir, previous one, sir.
Okay, the previous question. This question,
Sir,
quicksand condition.
your voice is not audible.
Okay, now
Yes, sir.
is it audible?
Sir, your voice is not clear, sir.
Okay, 1 minute. where we discussed about stoke, flow through capillary, classification of soil, consistency limits, flow of water through soil mass, velocity of settling particles. Anyone? No idea?
Velocity of settling particle.
Settling particle. Settling velocity means stoke. Okay. You might be studied him in classification, but don't answer that one. Darcy's laws flow through, soil flow through soil mass is your Darcy. Partially is a flow through capillary. That expression I gave, no, that is H equal to something D and all those things will come by partially. Okay, Poiseuille. Atterberg will come for consistency limit. Consistency limit. Classification of soil will be blank. Okay, now next one is this is finance modulus will not study here. Clay is an example of. Can anyone answer? Is it aquifer? Yields and holds? No. Aquitard? Slowly yielding? No. Aquifuse? No. Aquiclude? Holds but not yields. Not yields. Okay, therefore aquiclude. Next is the shear strength in plastic undrained clay is due to. Okay, don't worry, we'll discuss this question in later chapters because you don't know undrained clay, plastic undrained clay and all. Again, it will take time to explain. Next, which of the following expression represents the relative compaction where variables have their standard meaning? Relative compaction, you can write it here. See here, always confusing two terms are there. The first one is relative density. Relative density. Relative density is nothing but Emax minus E natural by Emax minus E minimum. And another one is relative compaction. Relative compaction. Relative compaction means just you are comparing the compaction. The compaction has happened very good, therefore gamma D max. Then this one is a gamma D natural. Okay. Now which one, how you can compare, which equation is right? Now which one they are asking? They are asking relative compaction. Therefore they are just, it is a relation between the compaction. Therefore field density by maximum lab density is the correct answer. Field dry density maximum, no, this is a maximum lab. No, this is meaningless. This is not required. Okay, A is the correct answer. Now in the flow over a length of 50 meter, the head loss is 6 meter occurred due to seepage. Hydraulic gradient is given by director. Length is 50 meter and head loss occurred is 6 meter. 6 by 50 is the answer. How much? Point 0.12?
0.12.
Right. Next. If a depth of moist sand in a cylinder is 15 centimeter and the depth of sand when fully inundated with the water is 12 centimeter, then what is the bulking of the sand? Bulking will study in concrete technology. Okay. Now, falling head permeability test carried out on a specimen having cross-sectional area 60, A equal to 60, height 15 centimeter, L is equal to 15, water level in a stand pipe diameter 0.5 centimeter, small a equal to pi by 4 into 0.5 square, drops from 100 to 40, H1 equal to 100, H2 equal to 40. In half an hour, T equal to 30 minutes, 30 into 60 seconds. What is the coefficient of permeability? Do it. Formula is AL upon AT ln H1 by H2. You might get A option. Am I right? Next question. Pick up the correct statement. Correct statement. Sand obtained from pits is washed to remove clay and silt. Correct. Sand obtained from flooded pits need not be washed before use. No, correct. Flooded pits. Seashore and seashore sand contains chlorides, uppu, and salt, which cause efflorescence. Correct. Therefore, D is the correct. If a White's ratio and discharge velocity of a soil is this much and this much, what is the velocity of seepage? Seepage velocity. Okay, very interesting. Seepage velocity by discharge velocity is equal to what? 1 by n. Right? Now, which one they have given? Discharge velocity is given. Seepage velocity they want. Therefore, discharge velocity, seepage velocity is equal to discharge velocity divided by n. And what is n? N equal to E divided by 1 plus E. Then what is E? E is 0.5. 0.5 divided by 1 plus 0.5. 0.5 by 1.5 is 1 by 3. 1 by 3 is 0.33. This is your 0.33 divided by 6 into 10 raised to minus 7. Hey, ulta. Right? V is 6 into 10 raised to minus 7 divided by 0.33. 0.33 means 1 by 3. 3 will go to the top. 6 into 3, 18. Therefore, D is the correct answer. Next, a falling head permeability test. Duration 3 hours. T is given. Initial head 100 mm is dropped to 350. H1, H2 is given. Diameter of the standpipe is given. Means small area is given. Length and diameter of the specimen is given. Okay. Then what is the coefficient of permeability? Directly you can solve it. But substitute everything in mm. Very important. Substitute everything in mm square, like that. Then you will get answer. Okay. Which option? Hope you will get this answer. Now, 10-meter thick confined aquifer gives the steady state discharge Q. The well of diameter 50 centimeter, well of diameter means R, due to pumping the height of the water in a well is dropped down to 15 meter to 10 meter. 15 meter to 10 meter, and the radius of influence is about 500 meter, that is capital R. Then this is a small height, capital height, and this is a small height. What is the coefficient of permeability? Do it. Formula. This one. Okay. Q is known, H is known, H is known, R is known, R is known. K is unknown. Okay. You can calculate that K. A is the answer. Sorry, where it is? No, correct. A is answer. Oh, sorry. Confined aquifer. No, it is. Confined aquifer means not that equation. This equation. This equation. I'm sorry. B is a confinement width of the depth of the confinement. Then you can substitute and get. Okay. Next. During the flow over length of 30 meter, the head drop is 5 occurred. Then the seepage 5 by 30. Hydraulic gradient 5 by 30. More on the 1.1 ಎರಡು 18. C is the correct answer. The ratio of compressive strength of a material saturated with water to that in dry state is known as. The ratio of strength of a material saturated, compressive strength of the material saturated with water to that in dry state. Thixotropy, Allah, because thixotropy is a phenomena of regaining the strength. Therefore, this is wrong. Coefficient of softening, coefficient of hardness. This I can say compressive strength of a material saturated to dry. They are comparing means it's a compressibility I can answer. But softening and hardness I can just remove. Next. This actually yesterday only we can solve this one. What is the capacity of density bottle used in generally for determination of specific gravity of fine grained soil? Fine grained soil density bottle in the laboratory as per IS is which one? 50 ml or 150 200? This is 50 ml is the right answer. Who is this is over. Which of the following is a method used in field to determine the permeability of soil? Oedometer is for consolidation, not for permeability. Wrong answer. Falling head permeability method is a lab method. Constant head permeability is a lab method. Pumping out well method is a field method. Limit of water content that tends to soil semi-solid to this one is over yesterday. Now this is very important. Am I audible properly? Audible, no? I have to assume yes.
Yes, sir.
Okay. Next, following statements are true about quicksand. It is only a condition but not a type of sand. Very good. It is a condition and a type of sand too. Now, quicksand condition reaches when critical hydraulic gradient is approximately equal to unity. This is somewhat good, but this word is there, no, that's why it is good. Approximately. Why approximately? Look at here. G minus 1 divided by 1 plus E is your IC, right? Now G usually how much it is? 2.65, 2.7, 2.72, 2.68, like that G value. If you make minus 1, then how much you will get? You will get a point, 1.68, 1.65, 1.7, like that you will get. Okay, denominator you check. Denominator 1 plus E is there. If White's ratio is 0.65, 0.68, 0.7, usually this is the value, no? Then if you substitute here, that will be nearly equal to 1, approximately equal to 1. Therefore, correct answer. Quicksand condition occurs more commonly in coarse grained sand and gravels than fine sand. This is wrong. Boiling action will takes place in fine sand, not in coarse and gravel, because in coarse and gravel the permeability is very huge. Boiling action you will not see. Okay, wherever that quicksand is there, no, you replace that word by boiling action, then boiling will be more in fine sand, no, therefore this is wrong answer. Then which one is correct? 193 is correct. Both 193 is correct. C option is right. The water content where further loss of moisture will not result in any soil volume. Yesterday happened this one, shrinkage limit. Which of the following statement are correct? Isochrones are curves of equal pore water pressure. Isochrones depict the variation of pore water pressure along the depth of the soil sample. Isochrones vary with time. Isochrone. See, in civil engineering, there are so many words with ISO. You know, ISO height, so ISO heightal, isochrone, so ISO bars, isometric, isotropic. You know, you do one thing. If you are sincerely preparing for competitive exams, about 15 or 20 words are there in civil engineering which are with ISO. Okay, by heart them, or have some logic behind the words and by heart them, because at least one question definitely that will come from this ISO. Right? Which is the answer? The correct answer is B. 2 and 3 only. Okay, now next, the phenomena in which clay is made loose and any ingredient to be added to it is spread out on top and turned up and down in a vertical direction is known as, what is this? Read it once again. We have to go by options only. Okay, weathering is not, weathering is erosion, cleaning is not, cleaning is not. Then what they are saying, they are saying that there is some soil and you will put something, some additives here, and after that you will put it down and you will put it up, you will put it down and you will put it up, no? Then what it is? It is a blending. Tempering is not, tempering will not come here. Which of the following factor does not affect the permeability of the soil? Answer. Does not affect the permeability of soil. The permeability of soil equation is E cube divided by 1 plus E C d square gamma W divided by nu. Therefore, grain size is there in the equation, property of fluid is there in the equation, White's ratio is there in the equation, volume is not there in the equation, not they are asking, therefore A is the correct answer. According to Terjgi and Peck, the ratio of D15 size of a filler material to D85 size of the base material, this comes in pavement design. They have included here. You can take answer B. Okay. Next, the height of the sample sand to be tested is 20 centimeter and height of the saturated sand is 16. Find the bulking of the sand. C. This yesterday we could have discussed consistency limits. Unconfined market we will discuss in shear strength chapter. Out of the cohesion limit, sticky limit, liquid limit, plastic limit, shrinkage limit, the most important in engineering practice are, out of these, cohesion limit, we don't have anything called cohesion limit, we don't have anything called as sticky limit, liquid limit we have, plastic limit we have, shrinkage limit we have. The most important in engineering practice are cohesion limit, plastic limit, liquid limit wrong, liquid limit, plastic limit, shrinkage limit right, cohesion limit, plastic limit, shrinkage limit, sticky limit wrong, plastic limit, shrinkage limit, cohesion limit wrong. B is the correct answer. Such questions are there, no? These questions are to eliminate those students who have not done anything, they have not worked anything, no? They have not studied anything. For them, they want to remove, no, from the list, elimination. Therefore, they will frame these questions. When you read everything, then you will come to know that cohesion limit in geotechnical, entire geotechnical career, I have not heard. Sticky limit also it is not there. Therefore, just remove them. Consider the different type of soil: fine sand, homogeneous clay, coarse gravel, silty clay. Arrange the soil in increasing order of their permeability, low to high. Huh. Which one is more permeable? Coarse gravel is a more permeable. Low to high, no? Low, low to high means first low you have to hold. Homogeneous clay and silty clay. Okay, these two, there is a tough competition between these two. Homogeneous clay and silty clay. Okay, silty clay means silt is there, particles are bigger in size, therefore this is the second place, this is the first place. First place is a C. Where is the C option?
Sir,
Okay, C and C.
B B is answer, sir.
B is answer. No, silty clay. Silty clay, that is the second player position. C is the option. F is fine sand and gravel. C is the option. Correct? Because you compare with the homogeneous clay and silty clay, which has a more voids. Silty clay will have a bigger pores because silt means bigger, no? That's why that will come in the second position. Homogeneous clay will come to the first position. Very low, high, high, high. Which of the following material is gap graded? This is already over. Activity of the soil. Okay. Yesterday I didn't give the definition for this one. We can have here. Activity of the soil is the ratio of plasticity index to, write it down. Activity is nothing but IP divided by percentage of clay. Clay percentage you can remember. Then where is that? Plasticity, the ratio of plasticity index to the percentage of compression strength, no. Liquidity index, no. Percentage of sensitivity, no. Percentage by weight of clay fraction is the right answer. This also we could have discussed in a previous day. Determination of plasticity index and the percentage of weight of a clay material finer than 2 micron. See here. Weight of clay material finer than 2 micron means C. IP means this is plasticity index means IP. Were done for 2 soil samples means what? They have discussed activity of these two. The ratio of plasticity index to the percentage of clay size particle for the sample A and B are given in the table. Okay. Now this okay. Sample A is 0.75 and sample B is 1.25. Then sample A and B classified as sample A is active, normal, inactive, active, normal, inactive, active, inactive. We should have some guidelines here to discuss this active and inactive. Right? Anyone can answer this one? Hmm? Write it down. Before that, you write this scale so that you can answer that very easily. Activity is equal to IP by C. Okay, na? IP by C. Write down. If A is less than 0.75, that is inactive. That is inactive. If A is in between 0.75 to 1.25, 0.75 to 1.25, that is normal. That is normal. Then if A is 1.25 to 1.25 to and greater, 1.5 and greater, that is your active. That is active. Then if A is greater or greater than the this one 1.2 16, sometimes it will be 16 also, sometimes it is more than 4 5 6 7 8 9 like that. That is hyperactive. In this option, which one is the correct answer? B is the correct answer. This is inactive and this is active. Greater than 1.25 is active, therefore B is the correct answer. This yesterday is over. The soil sample is tested for a plasticity index obtained from this is also over. Water content of a soil sample can be determined by shrinkage limit method, jar test method, sand replacement method, alcohol method. How many group of soil come under the Indian standard soil classification? 18. The unit weight of the soil sample is 20 and the water content is 18%. Dry density, first chapter. Over. Okay. If you have any doubts, you can ask. I have that other book. I have one more book. That book has some other multiple choice questions. Those questions I will click and send you in the group. You can solve them. Okay. How is the preparation going on? Is there any further assistance or further guidelines you can ask here, or otherwise later also you can call? Okay. Is there any difficulties in the preparation? This time I want everyone to pass this preliminary exam, paper 1. Everyone must pass. Okay. So that we can fully concentrate on paper 2. When we discuss paper 2, then only I will get a satisfaction of teaching, because paper 1 here just I am going in 1 hour or 2 hour, just I am going by one chapter, one module. It's very fast. That's why all of you, you have to come for paper 2. Like that you have to read for paper 1. Right? For that you can torture, you can ask questions, you can call me at any time. So that we can address your issues and you can crack the exam. Right? If you have any doubts, you can ask. Otherwise, we'll leave the meeting. Right. We'll leave the meeting. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.